I came to the Garvan a little over a year and a half ago. I've spent time on the faculty at Stanford University, and then for 16 years was in Canberra at the Australian National University. And I have to say that coming to Garvan has been the most exciting phase of my research career. It is an incredibly exciting place, a lot of very dynamic scientists, and every day there's something going on. And I think from the one story I'll tell you, you'll get a bit of a reason why I'm so excited to be here and why this is a special place. So the story I want to tell you about is about this little boy, Alan. So he was one of a small group of kids that we decided to sequence in the first few months after I arrived here. That was sort of the vision, that we have this incredible genome sequencing facility, one of the best in the world, here at the Kinghorn Centre for Clinical Genomics. And I thought, let's put this together with everything that we know about the immune system now, that I've learned and that my colleagues here in immunology, and with all these fantastic clinical immunologists around the city. So we got together with all of them and said, if you've got any cases that you just can't figure out how to solve them, let's just sequence their genome. Don't get too clever about it, don't overthink. We'll just sequence their genome, see if we can get to the bottom of it. So we did that, and Alan was one of the first 54. So let me tell you a little bit more about what we had to put together. So while it's me that's speaking, this is really a wonderful example of how the community, the science and medical community, has gotten together, and the community, all of you, because the catalyst that made it all happen was the Bill and Patricia Ritchie Foundation, who made a big bequest to the Garvan that enabled me to come and start this whole project. It wouldn't have happened without that, and it then enabled me to go out to all of these wonderful clinicians that you can see at the Sydney Children's Hospital, both at Randwick and Westmead, enabled me to work with the Kinghorn Centre and Marcel Dinger's team, with colleagues at Westmead Hospital, Millennium Institute, built my own team, and we've got this fantastic facility for being able to essentially make mouse avatars. So Alan, at the time that we sequenced him, he was 6 years old, and he was and had been very sick since he was 3. So when he was 3, he was first admitted to hospital at Randwick because his immune system, it turned out, was destroying his blood cells, his platelets that are critical for clotting, and so he was at very grave risk of bleeding to death. And his red blood cells, so he's terribly anemic. And as things went on, he, despite the best efforts of his paediatricians out at Randwick, who were absolutely fantastic, this was a case they couldn't get the upper hand in. And his immune system went progressively further and further off the rails, started to destroy his intestines and his lungs, and every drug that you usually would try and that would work wouldn't work for Alan. And so, in fact, by the time we got his genome sequence and made his diagnosis, he was back in intensive care, and it was really, he was on death's doorstep. The prognosis was very grave. So what happened was that essentially at the Sydney Children's Hospital, stimulated by what we could do with this wonderful bequest from the Ritchie family, we said, we sent the team out, and they consented the family and said, let's sequence the genome. We want to sequence both mum, dad, and little Alan. Sequencing was done on the Illumina X10 facilities that are here, and all that torrent of information that comes off a sequencer went into a very elegant and clever pipeline that's taken quite a few sophisticated computer programmers to develop, that essentially spits out the smoking guns to an expert clinical geneticist, Tony Rossioli, who made the diagnosis. And this is basically what he found. Looking at the computer screen, just one little part of the genome, and he basically found that Alan had, this green means that there's something terribly wrong with that gene in that spot. And he's got that from dad. Mum's normal in that spot. But over another part of the same gene, again, there's something terribly wrong. Black means even worse problem with the gene, and he's got that from mum. So it's just terrible bad luck. No relationship between mum and dad, just by chance they each happen to carry a different defect in the same gene, and 25% chance Alan, unfortunately, the cards didn't go his way. He's got no good copy of that gene. Now, one of the things that was tremendous about this is that this gene had just been discovered in the year before as a cause of a syndrome that actually, as we scrambled over the weekend once this diagnosis came out, it matched up perfectly with Alan's. And that had come basically from these kinds of genome sequencing efforts around the world. And so we were able to very quickly piece together every bit of information that was known about this condition. So already we were out of the fog of, gosh, what is going wrong with this little boy, to, well, we know what the gene is. We can already give the parents some clarity as to what's going on. And that's the first time in 6 years of what was really quite an odyssey for them. But the real miracle was this paper that had just come out literally 2 months before we got the diagnosis. Had this paper been delayed a little bit because the experts wanted them to do another experiment here, another experiment there, this story that I'm telling you would have had a completely different and very sad outcome. But this was fantastic because what this paper showed, it came from a doctor in Cincinnati at the Children's Hospital, Michael Jordan, who'd 8 years before had had a child very similar to Alan who couldn't figure out anything that would work and tried a new drug that was actually developed but didn't work terribly well for transplant rejection, but was approved for use occasionally for children with particular kinds of arthritis. And so he had access to that drug. He knew it was safe and had tried it in this one little boy 8 years ago and miraculously basically cured that little boy. And he thought, well, that's interesting. A year later, I had another case like that. Tried it again, same thing, and two exceptional responders and then a third. And it was only in the months before this paper that the technology became possible for Dr. Jordan in Cincinnati to sequence the genome of his 3 exceptional responder kids who all responded incredibly well to this drug, abatacept, and realised they all had the same gene defect. And it was the same gene defect which we'd just found in Alan. And so suddenly, the real miracle, which is happening more and more now because of all of the pieces of the puzzle starting to assemble and because of genome sequencing, suddenly Alan's diagnosis hadn't just told us what was wrong and connected with a whole lot of research, but it had connected us with a treatment. What was really satisfying to me was that it actually connected with a big body of research that I'd done myself over many years in figuring out some of the checkpoints that normally stop the immune system from doing what it was doing to Alan's blood cells. And I won't go through that except to say that it involved this molecule that's essentially a stimulator of the immune system and this brake called CTLA-4 that's a really important brake on the immune system. And basically what was happening and what all the science coalesced around in that eureka moment is that this gene that Alan's missing, LRBA, when it's missing, it's inside of the T cells in the immune system. And when it's missing, this brake on the immune system, CTLA-4, it disappears. And so suddenly the immune system loses its brake, and this molecule B7-2 then causes the immune system to basically go off the rails and start attacking blood cells and causing life-threatening disease. But the wonderful thing is that this drug, abatacept, is essentially that brake in the bottle. And so we put all of that together over a weekend and armed Alan's doctors with the information to make the case to try Alan on abatacept as an urgent thing the following week. And so this is what happened. So here's Alan's platelet count and red cell count. Here's where the diagnosis happens here. You can see this is the normal range. Things are very grave. We get the genetic diagnosis. This is not entirely working well, but and then we start the abatacept, and there goes his platelets and red cells. Over the following weeks, they came right back to the normal range. It really was an incredible thing. That was a year ago. He's a year out now, and it's the first time in his life. There's a wonderful video that was on the ABC a little while ago from his parents talking about what they'd been through and how this is the first time he's been able to play sport without any risk of bruising and bleeding to death. He's not completely out of the woods, and we're still doing an enormous amount of work in the laboratory to try and come up with a permanent cure. He's got to stay on the abatacept, but for now he's the best he's ever been since this whole odyssey began. So I might stop there. I think the point really I wanted to leave you with is medical research works. And most importantly, that this genome sequencing essentially gives us these GPS coordinates. When we apply these new tools to cases that are unsolved cases, suddenly we connect people with underlying molecular mechanisms and with targeted cures, like in Allen. It's still the exception rather than the rule, but as we learn more and more with these tools, this will happen more and more often. So I'll stop there, and thanks very much.